So I have uploaded the link of library called Paraview. In Mood, I think you can install it. Cannot see it. This is a library called Paraview. I think you can do it for the visualization of your results. For example, here we have a results called temperature flow. Oh, what's wrong? It's an open source library, so it's maybe not as good as the tech plot. So we read a file and then click the apply. And this is show the boundary, and we can read another, it's called the water. Then you can click here, reply, you can see here. And then you can change the visualization pattern. For example, if you choose Gaussian point, and then you get a 3D, like sphere. You can also change the, what to say, the radius of your point. Here, like this, and then you can click here to see the animation of your results. Also, you can change the color of your particles. For example, for your water, you can choose the density here, and you also can change the scale. This is standard automatic scale. You can change the exact scale here. For example, 0.99 and 0. And it's like this. And you also can change your peripheral contour here. So this basically the visualization. And then you can do other things. This is the dam break case. We will go to, I think, next lecture. Actually, I think I have talked it in the previous lecture. I studied how water column is propagated in a tank. Think about this. It's a 2D or 3D tank. It's a 2D. This is a solid wall. And you put a water here. And you have a gravity. Then under the gravity, the water will collapse. And as the existence of the bottom wall, it will propagate in this direction and this direction, and then impact on the right wall. And after that, it will go away along the right wall and then go up. And then after sometimes it will go down. I can show you some. There was some experimental here. This is the experimental study, and in the experimental they put a plate to stop the water initially, and then they after drift the plate very quickly, and then let the water propagate in the tank. You can see here, after the wave is back, and it shows a very very violent, how to say, the evolution of the surface, and it will impact again with the left wall or the right wall. And also during the evolution of the surface, there was some break of the waves here, you can see here, and also impact several times. Here, this case is, we can have another example, which have a very large hit of the water column. You can see it's much more violent impact phenomena is observed. And you can see a lot of water drops is observed after the impact. Also, the surface evolution is much more violent compared with the previous one. So I think in the next lecture, my colleagues Dong and Yaru will talk about how you can do this kind of simulation by using a particle-based method. And you can visualize it by yourself. And we also developed algorithm to do the visualization by our own, but it's a little bit complex. Maybe for this lecture, I will show you here. Where is it? Okay, it's not here. Anyway, so go back to the visualization here. Here we use several layer particles. You can see here it's not moving to mimic the wall, and we use also several, maybe 10,000 or 100,000 particles to simulate the water column. And we do not have a plate here because for the simplicity, I think it's not have a strong effect on the motion of the water. You can see here after it will first collapse and then propagate along the bottom wall and then impact on the right wall and go up, 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 up. So if the velocity is small here, and then it will form a backwater wave, and then it will collapse again. And here, there will be a re-entry wave, a jet actually forms here. Also, you can see there was a void region. Actually, in the experimental, we have not only the water, but also the air. So in this case, when the jet is formed, there will be some air is here. Then in this case, you can do some kind of multi-phase simulations. It can also simulate in our library. As here, after some times, it will re-entry the water, and here there was a second jet is formed after the wave re-entry. And then the jet will become larger and larger, and then it will collapse again. You can see at this stage, actually there was these particles can be seen as a drop, a water drop, and then it will collapse on the surface again and again, and it will form some break of the surface. And here you can see some impact here. And then there was an impact on the left wall. Again, the surface, now you can see here, the surface is very, how to say, it's not very noisy here. The surface is not small anymore due to the violent surface motion and violent re-entry and break. And then it will from a backward wave. Here you can see here. You can also observe a small jet here. And then it will, again, some jet is observed and then unpacked. Generally, it can see like this. I'm not sure how to enlarge it. Okay. We can change more the scale of the fine. Change the color. You can also change the color of the wall by using solid color here, black one, and you can also change the color of your background. I think it's wait a moment. Okay, anyway, you can find that by yourself. Also, we can see some stream to see the velocity. You choose here, this is stream here. I think they call streamline, and then apply. And choose which vector you are going to show. You can choose. It's not. It's not like it's graph. Sorry, it's graph. You can see how the acceleration of each particle looks like. We can just see the vector here. You can see which part of the particles has the larger vector of the velocity. And then go on and on. You can see a very large impact velocity is observed. Oh, this is ugly. Yeah. Okay, that's all. So today I only show the visualization of some results. And the next time, I think we will give the detail of what the code looks like to the simulation of this temperature flow. And so I think we can talk about the issues of your installation. So if someone is interested, you can stick here. Otherwise, you can leave. Okay. Thank you.